Hello guys, today we will discuss properties of convex polygons, how to compute some of the interior angles, exterior angles, number of diagonals and arc. In the first one, when we want to find what is sum of the angles, we can solve this in two different ways. One of them is just pick any random point, A, and connect with all non-neighbor vertices. Clearly, we will make up n minus 2 triangles. Here is just an example of hexagon, A6. This is first one, second one, third one, fourth one. And we know that sum of the angles in every triangle equal to 180 degrees. And if we have n minus 2 triangles, clear total sum will be 180 times n minus 2. And in our case, this will be 180 times 6 minus 2, 4. So the main idea is using the fact that if we sum up all of these small parts, they will give us in total sum of the angles in every polygon. Second solution is just choosing a random point inside the polygon and connect with all of the vertices. In this case, we will make up n triangles, but the problem is that we have added several angles. For example, in this case, if we have A1, A2, call this point O. Angle A1, O, A2 is additional, which was not angle of the polygon. So all of these small parts, they will be additional, call this alpha 1, alpha 2, alpha 6. And we are using the fact that sum of the angles in whole circle equal to 360 degrees. And as we have n triangles, total sum will be 180 times n, and we need to subtract this 360 part, which was addition. So we will get final formula 180 times n minus 2. And once we want to find the sum of the exterior angles, we are using the fact that sum of the interior plus exterior always equals to 180 degrees. Check this one, B2, B3, and so on. B1 plus B2 plus B3, B6. In our case, this can be written as 180 minus x1, where x1 is the interior angle here, plus 180 times 180 minus x2, and so on. And finally, we get 180 minus x6. And clearly, this can be written as 180 times 6 minus x1 minus x2 minus x6, which can be written as 180 times 6 minus 2. So the final formula will be 180 times 6 minus 180 times 4, exactly 180 times 2, so 360. And you can easily see that similar logic can be applied for any side polygon, because we are just using the fact that sum of the angles always equals to 180 times n minus 2. If you want to compute number of the diagonals in any n-side polygon, we can just pick any random point A and check how many diagonals can we make up where one of the endpoints will be A. You can see that this will be always equivalent of n minus 3, because A cannot be connected to itself and its neighbors. So A will take part in n minus 3 diagonals. And instead of A, we can choose any other vertices. So the formula will be n times n minus 3, but the problem is that in this case, we will count each diagonal twice, once for A and second time for B. And we need to divide this value by 2 to avoid overcounting. After this, there is also a bit different approach. If we consider how many different ways can we choose two vertices, A and B. This can be done and choose two ways, n times n minus 1 half. And if we subtract the sides of the polygon, so n sides, clearly this will give us the same result. N times n minus 1 half minus 2n over 2, which is clearly n times n minus 3 over 2. So this is second solution for computing number of diagonals. If we want to compute the area of the polygon, in most of the cases, this will be hard if circle cannot be inscribed in it. So in our example, if circle can be inscribed inside the polygon, so which means that this circle is tangent to all of the sides. If we pick the center, call this one A1, A2, A6. What's the property of tangent? It means that this is 90 degrees here. And once we want to compute the area of angle triangle A1I A2, this will be just inradius times A1 A2 divided by 2. Similar logic will work for A2I A3 when we get R times A2 A3 divided by 2. And clearly we can do same logic for A3I A4, A4I A5, and A5I A6, and A6I A1. And if we take R over 2 out of brackets, we get A1 A2 plus A2 A3 and so on, all of the sides. Finally will be A6 A1, which is clearly the perimeter of the polygon. So the main formula will be R times perimeter divided by 2, which is called semi-perimeter. But in this case, if you want to use this formula, circle must be inscribed inside polygon. Otherwise, we cannot do it. One of the most well-known examples of polygons are regular polygons, when all of the sides and all of the angles are equal to each other. In this case, if we have polygon inscribed in a circle, and this is not only for regular polygons, but in most of the cases we will see regular polygons. Any questions? If it is even side regular polygon, circle can be also inscribed in it. And their center of the in circle and circumcircle will coincide each other. Call this point O. And if you want to find a relation between in center, inradius and circumradius, we need to compute what is angle A1 OK if K is the base of the altitude from O to A1 A2. We can easily see that angle A1 OA2, this will be just 360 divided by n because of symmetry, and all of these angles will be same. Regular polygon definition. Everything is symmetric. And angle A1 OK, this will be just half of A1 OA2, which is clearly 180 divided by n. In the small part alpha equals this. Right, the circumradius equals A1O, while inradius equals OK. And clearly, cosine alpha will be equivalent of OK divided by A1O. So, if you want to find the relation between them, we just need to find what is angle alpha. Angle alpha will be cosine 180 over n. In most of the cases, this will be n equals 6 or 4 or something similar. It's less likely that we will need to compute some ugly cosines because they are very hard to compute. And based on this, we will easily find what is the relation between inradius and xradius. This was all I wanted to discuss about polygons. If you have any questions or formulas you are interested in, please write in the comments, and don't forget to like and subscribe my video.